to start. Today, we do a bunch of problems using the fundamental theorem of calculus. Okay, so a few announcements. You're gonna have homework due Monday night. You have a quiz that's gonna be due Friday night. I will open the quiz after this class. It's over stuff that we're doing today. Okay. So, any questions about those two announcements? All right, so here's a reminder of the first fundamental theorem of calculus. Okay, so if capital F is any antiderivative of the continuous function little f of x on the interval a to b, then the integral from a to b of little f of x is equal to capital F of b minus capital F of a. So this can be any antiderivative. So when you're doing a definite integral, you don't need the plus c. And here's why. If I'm looking at the integral from a to b of f of x with respect to x, well, if I add on the c, I'm going to get f of b plus c minus f of a plus c. But then this is f of b plus c minus f of a minus c. So the constant just goes away. So when you're doing definite integration, you don't need to include that constant. Okay. So the proof of this relied on essentially rewriting f of b minus f of a in a very tricky way, and then using the mean value theorem for differentiation. Okay. So we're going to look at several examples today of finding definite integrals using the fundamental theorem of calculus. So first off, here we go. We're going to find the integral from minus 2 to 3 of 5x to the fourth minus 4x plus 5. All right. Integral from minus 2 to 3, 5x to the fourth minus 4x plus 5. All right, so whenever we're finding a definite integral, first thing, and it's the integral of a sum, first thing you usually want to do, especially if it's a polynomial, is break this up into its individual parts. You want to write this as the integral from minus 2 to 3 of 5x to the fourth dx minus the integral from minus 2 to 3 of 4x dx plus the integral from minus 2 to 3 of 5 dx. Okay. You can break up that integral because you can break up differentiation the same way. And integration and differentiation are opposite processes. Okay. So the integral of 5x to the fourth, this is a bunch of powers of x. So something that I've been using, but something I'm going to write out explicitly right now is the power rule for integration. Okay, and that says that the integral, the indefinite integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus some constant. Now, remember, if I'm doing an indefinite integral, I do need the plus c. Okay, so this holds for n not equal to 1, or minus 1 rather, sorry. For n not equal to minus 1. So this is what we're going to use here. So the first integral, what's the integral of 5x to the 4? Well, really, I can pull the 5 out in front, right? So what's just the integral of x to the 4?
X to the 5th over 5.
Perfect. So here I'm going to get 5 from there, and then x to the 5th over 5 from the in-depth or from the power rule for integration. Okay, and then minus, all right, I'm going to, again, pull the 4 out in front. So what's the integral of just x with respect to x?
So hold on, the in is the exponent, so that's how they got 5 on the bottom.
Yes. Yeah. So what do we get when we integrate just x with respect to x?
Maybe x squared.
Perfect. So I'm going to get minus 4 from that constant that's just out in front times x squared over 2 plus, well, again, I can pull this 5 out in front. And this is the integral of 1 dx. So what's the integral of 1 with respect to x? What would n be for this? This is still technically a power rule. So
Would
what
it be
is
0?
Yeah, n is 0 here, right? 1 is x to the 0. So then what's the integral of 1? Perfect. I just get x. This 5 out in front comes along for the ride, plus x. So now I'm going to plug in I'm going to show you some useful notation for writing out plug in minus 2 and 3 and subtract. Okay, there's some useful notation that says exactly this. Okay, so well, first I'll simplify before I do that. This is 5 over 5. I'm going to get x to the 5th minus 2x squared plus 5x, right? So really I want to plug in minus 2 and 3 and subtract there. Okay, so I'm going to plug in the top bound first. So I'm going to plug in 3 first. So I'm going to get 3 to the 5th minus 2 times 3 squared plus 5 times 3. So there's the top bound plugged in. And then I'm going to subtract off when I plug in the lower bound of minus 2. So I'm going to get minus 2 to the 5th. So minus 2 to the 5th. And then we have a minus 2 times minus 2 squared plus 5 times minus 2. Okay. Questions on that? Okay, so 3 to the 5th, that's 81 times 3. 81 times 3 is what, 243? 243 minus 2 times 9, so minus 18, plus 5 times 3 is plus 15, minus 2 to the 5. Well, 2 to the 5 is 2, 4, 8, 16, 32. And so is it plus or minus 32? Minus 2 to the 5. minus, right? I'm taking minus 2 to an odd power. So I'm going to have minus 2, 4, 8, 16, 32, minus 32. And I'll have minus 2 times, well, minus 2 squared. What's minus 2 squared?
4.
Yes. Plus 4. Why is the last term of the question not considered an integration? It is an integration of a constant, but you can still use the power rule. So minus 2 times 4, and then 5 times minus 2 is minus 10. Okay. So this is going to be 243 minus 18 plus 15. Well, minus 18 plus 15 is minus 3. So I'm going to get 243 minus 3 gives me 240 from these guys. Minus, well, minus 32 minus 8. That's minus 40. And then minus 10 gives me minus 50. And you want really, when you subtract off that second f of b minus f of a, always put the minus f of a, put that in parentheses, because you're going to drop a negative for sure somewhere along the line when you're doing one of these problems. And it's annoying to do. Okay, so then we get 240 minus 50. Okay, and so 240, that's really 240 plus 50, which gives me 290. Okay, so by the fundamental theorem of calculus, the integral from minus 2 to 3 of whatever we were doing, 5x to the 4th minus 4x plus 5 dx, this is equal to 290. So notice x to the 4th, that's something that doing with the Riemann sums would have been awful. Okay, so this is a much nicer way to handle these definite integrals. Okay, questions on this? Question in the chat. Usually the integration of constant is c times, yeah, if you work out the integration of the last part, it comes out to be 1 times 5 is what that's contributing, but you can also think of it as the power rule. It's equivalent. Any other questions? All right, evaluate the integral from 0 to pi of sine of theta with respect to theta. All right, so again, I just need to find some antiderivative of sine of theta. So what function do you know that when you take its derivative, you get sine of theta?
Cosine.
Cosine theta. Let's check and see. Oops. We want to check and see, does the derivative with respect to theta of cosine of theta, does that equal sine of theta? Cosine of theta starts with a c, so that gets a negative sine of theta, right? So we're not far off, but the integral of sine of theta isn't just cosine theta. What should it be?
Negative cosine theta.
Negative cosine theta, right? So if I differentiate the negative cosine of theta, then I get positive sine theta. So that tells me an antiderivative of sine of theta is minus cosine theta. Okay, so we're going to get then the integral from 0 to pi of sine of theta with respect to theta. Well, that's negative cosine of theta. And then we're going to plug in theta equals pi and theta equals 0 and subtract. So then when I plug in theta equals pi, I'm going to get negative cosine of pi. And then I'm going to subtract off when I plug in theta equals 0. I'm going to get minus negative cosine of 0. Okay. So again, this is another example where if you don't put your function in parentheses, I guarantee someone's going to drop a negative at some point. Okay. So what is the cosine of pi? Who knows? Ah, perfect. Yeah. This cosine of pi is -1. So I'm going to get, when I simplify this, I'm going to get -1. There's cosine of pi. And then minus, what's the cosine of 0? +1. Very good. So minus from that minus that's already there, 1. So lots of negatives, but they all come out. Negative times negative gives me +1, minus -1 gives me +1, and so that is equal to 2. Okay. So the integral from 0 to pi of sine of theta with respect to theta, that's just equal to 2. Which is pretty amazing. Questions on this one? All right. So some general guidelines for using the fundamental theorem of calculus. Okay, so if you can find an antiderivative of little f, and that's not always going to be the case. Sometimes it's very difficult to find an antiderivative. That's actually what most of Calc 2 is going to be about, is developing techniques to find antiderivatives. Okay, so provided you can find an antiderivative of little f, you can evaluate a definite integral without having to use a limit of a Riemann sum now. So when applying the fundamental theorem of calculus, this notation right here is going to help me to keep from writing plug in x equals a and x equals b and take a difference over and over. Okay, so that notation, capital F of x, line b a, and sometimes I'll write x equals b up top and x equals a down bottom, especially if there's more than one variable going on, so I know exactly which variable I'm plugging in for. Okay, this just means take f of b and subtract off f of a. Okay, that's all that means. Okay, so is there any questions about that? Cool. So it's not necessary to include the constant of integration, like I said, because again, when you take the difference, if you do include the constant of integration, the c will cancel out with the minus c. Okay, so when you're doing definite integrals, you do not need to include the plus c. All right. So a word of warning: you're going to want to do every definite integral now by using the fundamental theorem of calculus, and you're going to convince yourself when you see a problem, you're going to convince yourself that you have the right antiderivative to use in the fundamental theorem of calculus, and that's not always going to be the case. Sometimes the fundamental theorem of calculus isn't very helpful. Okay, so as an example, in trying to find the integral from -1 to 1 of the square root of 1 minus x squared with respect to x, the fundamental theorem of calculus is not very helpful, because if you need to find an antiderivative of square root of 1 minus x squared, well, everyone thinks that they can find it. Everyone thinks, well, I'll just add 1 to the 1 minus x squared to the 1/2, and then I'll I'll look at it and that'll be right. No, it's very difficult to find an antiderivative of the square root of 1 minus x squared. Okay. You can't really use the fundamental theorem of calculus on this. Actually, we'll find out in Calc 2 that there is a technique you can use that's way harder than you need for this. So who knows, how should we evaluate this integral? Think back to what the integral actually means.
Calculating the area.
Yeah, we're trying to find the area under a curve, right? And I kind of showed you this problem the other day. So if I'm trying to find the area under a curve, well, let's look at the actual curve that I'm trying to find the area under. I'm looking at the area under y equals the square root of 1 minus x squared, right? So if I square both sides, I get y squared is equal to 1 minus x squared. And then if I add x squared to both sides, I'm going to get x squared plus y squared is equal to 1. And what is that equation?
Circle.
Yeah, this is a circle of radius 1, right? So a circle of radius 1. These are all 1, 1, 2, 3. Okay, and which part of this circle am I actually looking at? I'm looking at y equals the positive square root of 1 minus x squared. Yeah, I'm looking at the top half because I'm looking at the positive square root, right? So really, I want to know what is, oh gosh, what is this area here? And what is that area? This circle has a radius of 1. So
Just pi over 2.
yeah, very good. The area of the whole circle is pi times 1 squared. So the area of the upper half of the circle is pi over 2. Okay. Any questions on that? So the fundamental theorem is going to be great for 99% of the problems I give you. If ever you're having a really, really hard time trying to find an antiderivative, well, then maybe I'm trying to trick you. Maybe you need to look at the actual curve that you're finding the area under. Okay. So, questions? Why pi over 2? Pi, the area of the circle of radius 1 is pi times 1 squared, which is pi, and we want half of that, so pi over 2. All right, so let's look at another example. Evaluate the integral from 1 to 4 of 3 times the square root of x. All right, you guys tell me. Lead me. What should I do first? Yeah, I think pulling constants out in front, again, 99% of the time is going to be a really good idea. So this is equal to 3 times the integral from 1 to 4 of the square root of x dx. All right, now what should I do?
Turn like x or square root of x.
Yeah, hopefully we've all seen by now that in calculus, we don't ever actually write the square root symbol. We usually just use x to the 1/2, right? I might write the square root symbol to check and make sure that you know that the square root of x is x to the 1/2. But for calculus purposes and the power rule, we really like x to the 1/2 better. So what next? power rule. So I'm going to get 3 times, what does the power rule say the antiderivative of x to the 1/2 is?
X to the 3/2 over 3/2.
Perfect. X to the 1/2 plus 1. So that's 1/2 plus 2/2. That gives me x to the 3/2. I'm going to divide that by 3/2, right? So this is an antiderivative of 3x to the 1/2. So I'm going to say I want to evaluate this as x equals 4 and x equals 1 and take a difference. Okay. So before I actually plug in, I'm going to do a little simplifying first. If I'm finding x to the 3/2 divided by 3/2, well, divided by 3/2 is a little annoying. I'm going to flip that and turn that into a multiplication, right? So this is going to be the same thing as 3 times 2/3 times x to the 3/2. Evaluate at x equals 4, subtract off when x equals 1. Okay. And then lastly, you can cancel the 3 with the 2/3. Or with the 3 in the bottom. Okay. So we then want to evaluate the integral of, or not the integral, sorry. We want to evaluate 2 times x to the 2/3, or 3/2 rather, sorry, 3/2. 3/2 at x equals 4 and x equals 1. So that's going to give me 2 times 4 to the 3/2. There's when I plug in x equals 4. Minus, well, when I plug in 1, I'm going to get 2 times 1 to the 3/2. Right? What is 4 to the 2/3? Or sorry, 3/2. Well, what's 4 to the 1/2? 2. And so then that 4 to the 3/2, that's the same thing as 4 to the 1/2 to the 3rd. Okay? These are the same thing. Minus 2, 1 to the 3/2 is clearly 1, right? So 4 to the 1/2 is 2, so I'm going to get 2 times 2 to the 3rd, right? And then minus 2. So that's going to give me 2, 4, 8, 16 minus 2. Which gives me 14. Questions on that? Cool beans. So the power rule is going to be one of your best friends. Just like with differentiation, I mean, we differentiate a lot of polynomials and rational functions. Those aren't the only functions in the world, but they're definitely great for examples. So definitely get used to the power rule for integration, just like you got used to the power rule for differentiation. Okay. All right, evaluate the integral from 0 to 2 of the absolute value of 2x minus 1. Do you know any functions where you take the derivative and you get the absolute value of 2x minus 1? The answer is no. It's a weird a weird thing. Anytime an absolute value is happening in an integral, you need to look closer at what's really happening. So let's get a sketch. The fundamental theorem of calculus kind of lets us bypass sketching things most of the time. But here, I need to look a little closer because I don't know an antiderivative of the absolute value of 2x minus 1. Okay, so let's look at the absolute value of 2x minus 1. Let's sketch that. Awful. Straight line. Nailed it. Doesn't matter if it's straight, if it's slanted. Good. Okay. So we're looking at this specifically between x equals 0 and x equals 2. Those are the only two, that's the only interval that I need to plot this on. Okay, so let's go 1 and 2. So the absolute value of 2x minus 1. Well, this is equal to just 2x minus 1 if 2x minus 1 is greater than 0, right? I mean, the absolute value of something is just that thing if that thing is positive. And what is it equal to if 2x minus 1 is less than 0?
Something that's less than 0.
Mhm.
Absolute value.
Yeah. Yeah. So if something is smaller than 0 to find its absolute value, then you can just multiply it by -1, right? Does that make sense to everybody? So we're going to get negative 2x minus 1 if 2x minus 1 is less than 0. Okay, this is the definition of the absolute value function. Okay, so if I simplify this a little bit, I'm going to get 2x minus 1 if, well, if 2x minus 1 is bigger than 0, that's not very helpful for me to graph it, right? So if 2x minus 1 is greater than 0, then what does that tell me about x? What can I do with that inequality? If 2x minus 1 is bigger than 0, then what can we say about x? Do what?
X is positive.
X is positive. I can say even better than that. I want to use this to tell me something about x. Well, if you just saw this out in the wild, what would you start to do with it?
X is greater than 1/2.
Yeah, x is greater than 1/2. So I would say I would add 1 to both sides. I would get 2x is greater than 1, and then I would divide by 2. X is greater than 1/2. Okay. So that means the absolute value of 2x minus 1, well, that's just 2x minus 1 if x is bigger than 1/2. And it's, if I distribute the negative, 1 minus 2x if x is, well, if you do the same thing with this inequality, you'll find out that x has to be less than 1/2. Okay. So if I come over and graph this, well, I'll start with the x less than 1/2. So I'm graphing this between x equals 0 and x equals 2. So when x is 0, I'm just getting 1 here, right? So when x is 0, I'm just getting 1. And then when you look at the slope, minus 2 over 1, that tells me that there's this portion of, sorry, that was x equals 1. So that tells me, if this is 1/2, that tells me there's this portion of the graph between x equals 0 and x equals 1/2. Okay. And then the rest of this graph, well, 2x minus 1, you can just say, well, now I know that this point is on this graph. I'm plotting 2x minus 1, so it has a slope of 2, right? So I'm going to go up 1, 2, and over 1. And I'm looking at this now, right? So really this question, find the area under the curve y equals the absolute value of 2x minus 1. Really the question just turns into find the area of these two rectangles. So we could phrase it like that, or we could use this definition of absolute value of 2x minus 1 and actually still use the fundamental theorem of calculus. And how are we going to do that? Well, let me add a page. The integral from 0 to 2 of absolute value of 2x minus 1 with respect to x. I'm going to rewrite this as the point where everything is breaking for this is x equals 1/2, right? At 1/2, the absolute value sort of switches, right? So I'm going to write this as the integral from 0 to 1/2 of the absolute value of 2x minus 1 dx plus the integral from 1/2 to 2 of the absolute value of 2x minus 1 dx, right? So that was one of those properties of integrals I showed you the other day. And it's pretty intuitive. It says if you want to find the area of a whole shape, you can add up pieces of the area, right? But now, when I'm looking at the integral from 0 to 1/2, what is the absolute value of 2x minus 1 between x equals 0 and x equals 1/2? Well, between x equals 0 and x equals 1/2, you're looking at this line here, right? So between x equals 0 and 1/2, we're actually looking at the absolute value of 2x minus 1 is 1 minus 2x. Okay, so I can replace the absolute value of 2x minus 1 on this interval with its definition. Does that make sense to everybody? Plus. And then the second integral, well, the absolute value of 2x minus 1 on the interval 1/2 to 2, well, now we're looking at this line, right? So the absolute value of 2x minus 1 on that interval is just 2x minus 1. Okay. Questions so far? Okay, and now I can just use the fundamental theorem of calculus on each of these integrals. Okay, so you might feel like fundamental theorem of calculus is overkill for this problem, and it is a little bit, but later we're going to see an example where we're integrating the absolute value of something, and so this is an important example to see with an easier example. Okay, so the integral, so first of all, what's the integral of 1 minus 2x, or an antiderivative of 1 minus 2x? Well, what's an antiderivative of just 1?
X.
X, very good. Minus, what's an antiderivative of 2x?
X squared.
Good. x squared. So this piece right here is just that. And then I'm going to get plus. This piece, well, I already found these antiderivatives. Oh, there we go. These antiderivatives just in the opposite order. So the integral, the antiderivative of, or an antiderivative of 2x is just x squared. And then an antiderivative of 1 is just x. So into this, I'm going to plug in x equals 2 and x equals 1/2 and subtract. Questions here? Okay, so when I plug in 1/2 into this first part, I'm going to get 1/2 minus 1/4. What do I get when I plug in 0? I just get 0. Yeah, very good. So I'm going to get minus 0. So that's this piece plus. Now we'll do this piece. Well, when I plug in 2 into, come on. When I plug in 2 into this, I'm going to get 2 squared is 4 minus 2. And then I'll subtract off when I plug in 1/2. So I'll get minus 1/4 minus 1/2. Okay. Questions so far? And now the rest is just arithmetic. And I know sometimes the arithmetic is the hardest part, but in theory, it's not that bad. So 1/2 minus 1/4, what is that?
1/4.
1/4, very good. You're gonna get 1/4 minus 0. I'm not gonna write that. Plus 4 minus 2 is 2 minus 1/4 minus 1/2. Well, that's minus 1/4, right? So I'm gonna get 2 plus 1/4. Okay. So I get 2 plus 1/4 plus 1/4. That's 2.5 or 2.5. Or if you want, you could write it as 5/2, either way. Okay, so again, fundamental theorem of calculus was definitely, I'm not going to argue with you, it is definitely overkill on this problem. But later we're going to be looking at integrating things that aren't just straight lines, where we do still need to look at the absolute value of that thing. And so it's important to know how to handle that when it comes up. And this is how we would handle it if it wasn't just a straight line. Okay. So any questions on this? All right, find the area of the region bounded by the graphs of the equations y equals negative x squared plus 4x and y equals 0. All right, this question almost exactly comes up on the homework, so be aware. So the area of the region bounded by the graphs of the equations y equals minus x squared plus 4x and y equals 0. What does that even mean? Well, we should probably draw a graph to see what's happening, and I'll be a little more accurate on this graph. So I'm going to get some graph paper going on. Give me a straight line. Come on. Perfect. All right, so there's that. There's that. All right. X and Y. So let's start drawing some of these graphs. I'll start with y equals 0. That's an easy one. Done. Y equals 0 is the x-axis. Boom. Halfway there. All right, so y equals negative x squared plus 4x. Well, this is a parabola. It opens down, right? Negative x squared. And something that might be useful to plot this is to find its zeros. So if negative x squared plus 4x equals 0, then I can factor an x out of the left. I'm going to get x times negative x plus 4 is equal to 0. So what is x equal to? 0.
And negative 4.
4.
And positive 4, yeah. If negative x plus 4 is 0, then x has to be positive 4. Very good. So we'll come back over here. This parabola opening down has a 0 here, and at 1, 2, 3, 4. And so it looks something like this, okay? So the region bounded by the graph of y equals 0 and y equals negative x squared plus 4x, what would we say that region actually is? There's a bunch of different regions happening here, right?
Is it like the little like hump that's above the x-axis?
Very good. It's this, when they say bounded, they mean the region that is finite. Technically, there's a region beneath this, right? This is still between x equals 0 or y equals 0 and this curve, but that region is unbounded, right? It goes on forever down here. We don't want that. We want the region that has as its boundary these curves, okay? And that's exactly this green region here. Okay, so then how can I translate this question into an integral problem? Well, let's look at the graph. I want to translate into the integral of some function with respect to x. Good. And what's the function I'm integrating? Perfect. Negative x squared plus 4x, right? Because this green region is just the area underneath the curve, y equals negative x squared plus 4x. And we're doing that between x equals 0 and x equals 4. So the translation of this problem into a definite integral is just this. Okay. So let's try to compute this really quick. Well, what's the integral? So I'm trying to find the integral from 0 to 4 of negative x squared plus 4x. Well, what's the integral of, or an antiderivative of negative x squared?
Two-thirds x cubed.
I agree with x cubed. And I agree with the over 3, but there's not going to be a 2 out in front. It's just going to be negative x cubed over 3. Because we can break this up as negative 1 times the integral from 0 to 4 of x squared dx plus 4 times the integral from 0 to 4 of x dx. Okay. So negative x cubed over 3, and then plus 4 times what? X squared. Anything else? Close. X squared
Over 2.
over 2, yeah. You have to divide by your new exponent. Okay. So I'm going to plug in 0 and 4 into this. Okay, and I'll do that in my office before I upload this. But this is, I mean, we're 90% of the way there. So does anyone have any questions about anything we covered today so far? The next example sort of leads us into the second fundamental theorem of calculus. So tomorrow we're going to talk about the second fundamental theorem of calculus. We'll pick up right where we left off because these notes, I knew I wouldn't get all the way through them, but they're intended to be picked up. Okay, so if there's no questions, have a great day. Please wipe down your desks as you go, and I'll see everybody tomorrow.
Thank you.
Thank you.
Thank you.
So when